This lesson shows you ways to debug and troubleshoot a VI. If the Run button appears broken, it means that the VI contains errors that prevent your VI from running. You must fix these errors before you are able to run the VI. When the Run button is not broken, it means you can run the VI. To find out why a VI is broken, you can view a list of errors by clicking the broken Run button. The Error List dialog box lists all of the errors in the VI and provides detailed information about the problem. Let's take a look at this example of a broken VI. First, I click the broken Run button to view the list of errors. We can see that one of the errors states that you have connected the output of an add function to a control. Let's double-click the error to find its location on the block diagram. There it is. I can see that I've connected the output of the add function to a control terminal, which won't work because they both output data to the block diagram. I can fix this by changing this control into an indicator, and see it disappears from the error list. The next error in this list is that the divide function contains an unwired input that is required. Let's find the error by double-clicking it. If I wire this numeric constant to the required input of the divide function, I fix the error and it disappears from the list. The last error states that two terminals of different data types have been connected together, which won't work. This is an error due to mismatched data types, because we have a Boolean output wired to a string input. As I examined this, I realized that the in-range string indicator should probably be a Boolean indicator instead, since this indicator will only have two states, either in range or not in range. Notice that when I replace this string indicator with a Boolean indicator, I have fixed the mismatched data type error. And now that I've fixed all my errors, the Run button is no longer broken, and I can run my VI. Sometimes a VI is not broken and runs, but produces unexpected or incorrect data or behavior. Then you need different debugging tools and techniques to identify and correct the logic problems. Use the Highlight Execution button to view an animation showing the movement of data on the block diagram from one node to another. This can help you get a better idea of the order of execution in your VI. You can also see the data values being passed along each wire. If the VI runs more slowly than expected, confirm that you've turned off execution highlighting in sub-VIs. You can use the single stepping buttons to see how data moves through your diagram, one node at a time. Each time you click a single step button, only one node on your diagram will execute. Another debugging tool is a probe. Use a probe to check values on a wire as the VI runs. If you have a complicated diagram with a series of operations, and any one of which might return incorrect data, you can use multiple probes to read the data values passed along any wire to check if your code is working the way you expect. Breakpoints are debugging tools that allow you to pause execution at specific locations that you designate in your program. When the VI reaches a breakpoint during execution, the VI pauses, and you can take the following actions. Single step through the execution using the single step buttons, probe wires to check intermediate values, change the values of the front panel controls, or click the resume button to continue running to the next breakpoint or until the VI finishes executing. I'm able to run this VI, but the results of the VI do not look correct. So now I'm going to debug this VI. First, I'll use the Highlight Execution button to animate the flow of data through the block diagram at a slower rate. Second, I can use the single stepping buttons to execute a single node at a time. Click the Step Over button to start single-stepping through the VI. Since highlight execution is still turned on, execution highlighting still shows the flow of data from one node to another. I can click the Step Over button after each node to step through the entire diagram. When I step over the last node in the diagram, black lines appear. I can then click the Step Out button to finish running the VI. Third, I can probe the specific wires by right-clicking a wire and selecting Probe. The Probe Watch window shows an item for each probe. Now I'll run the VI. Notice that the Probe section has updated to show the latest probe values. By examining these probes, I can determine that Probe 1 shows the correct temperature in Celsius, and Probe 4 shows an incorrect value for temperature in degrees Fahrenheit. This means the mistake in this VI must occur in the nodes between Probe 1 and 4. On closer inspection, it looks like our constants are incorrect. Let's fix that. The next debugging tool I'll show is the breakpoint. I'll set a breakpoint on the Add function by right-clicking it and selecting this. Notice that a red line appears on the Add function. Now when I run this VI, the VI pauses when it reaches the breakpoint. I can start using other debugging tools, such as highlight execution and single-stepping. When finished, I can either disable the breakpoint or clear the breakpoint if I no longer need it. When you debug code, be aware that floating point operations can return symbolic values to indicate faulty computations or meaningless results. Symbolic values include NaN, or not a number, plus infinity, and negative infinity. NaN occurs when invalid operations take place, such as taking the square root of a negative number. Infinity occurs when an operation, such as dividing a number by 0, takes place. In this example, the VI tries to access a DACMX channel, start a task, read data, and clear the task, but the DACMX channel does not exist. How can you handle and report this error? By default, LabVIEW automatically handles any error when a VI runs by suspending execution, highlighting the node where the error occurred, and displaying an error dialog box. In the error dialog box, each error has a numeric code to identify it, and a corresponding error message to display to the user. This is called automatic error management. Let's see what happens when we run this piece of code, which generates an error. When the DACMX create channel tries to create a task with a channel that does not exist, the node results in a runtime error. Notice that automatic error management immediately suspends execution at any node that has a runtime error and launches the error dialog box. This dialog box has two options, either to continue executing the VI or to stop the VI immediately. Programmatic error management. In most cases, instead of relying on automatic error management, you should use programmatic error management so that you can control how errors are passed and reported. To use programmatic error management for a node, wire its error output to the error input of the next node. If a node executes without any error occurring, the node will pass no errors on its error output wire. However, if a node executes and has a runtime error, the node passes that error to its error output wire. Most nodes will skip execution if they receive an error on their error input. However, shutdown nodes, like DACMX clear task and close file, will typically try to execute and shut down resources even if they receive an error on their error input. At the end of your VI, you can connect the error wire to a simple error handler VI, which reports error details in a dialog box if an error has occurred. Now let's turn on Highlight Execution to see the behavior of programmatic error management. Notice that when the DACMX Create Channel node has a runtime error, it passes the error along the error wire. The other nodes continue to pass the error along the error wire until the error gets the simple error handling VI, which reports the error information to the user in a dialog box. By using programmatic error management, we are able to manually control how and when to report the error. If I now select the DACMX channel, which supports the thermocouple, and run the VI, notice there are no longer any errors, so the simple error handler VI does not display. An error wire is an error cluster data type, which consists of status, code, and source items. Status is a Boolean value that reports true if an error occurs. Code is a 32-bit signed integer that identifies an error numerically. Source is a string that identifies where the error occurred. Many nodes include error inputs and outputs to allow for programmatic error handling. If no errors occur, the node executes normally. If there are errors, the node that detects the error does not execute and passes the information to the next node. The next node does the same thing. At the end of the execution flow, you can place a simple error handler VI, which displays a dialog containing information if an error has occurred. Here's a summary of what you've learned in this lesson.